Welcome to Structural MD Podcast, episode 004, Laser Sintering. I am your host, James Hilligus. Real quick, before we jump into the episode, I just want to throw it out there that any of the links mentioned in today's show, contact information, etc., can be found on the show notes at structural-md.com/P004. I'm sure I will mention that link several more times throughout the show. I know you guys are a lot of busy professionals who are looking to upgrade your skills, looking to learn more about this new and ever-captivating technology of 3D printing, and chances are you're probably driving, at the gym, etc., and you can't quite write down everything I'm saying. So go ahead, take a look at the show notes. There will be a small PowerPoint slide, videos, pictures, links, contact information, etc., and you can always contact me via the website. So what is laser sintering? Well, laser sintering is a process where a thin layer of plastic powder is selectively melted by a laser. Like with all things in 3D printing, the parts are built up layer by layer, contained in a powder bed. As you will come to learn in 3D printing, we love to use synonyms. For laser sintering, one of the other synonyms or common terms you will hear is selective laser sintering, often abbreviated SLS. We also love abbreviations, never forget that. So how does laser sintering work? A laser sintering machine will coat a layer of plastic powder onto a build platform, which is melted by a laser, or multiple lasers to speed up that process. The build platform will be then lowered, and the next layer of plastic powder will then be laid on top. By repeating the process of laying out powder and melting where needed, the parts are built up layer by layer in the powder bed. Laser sintering does not require any support structures. This is huge. That means your post-processing is a lot shorter. You don't have to go in and remove the support structures via a material, grinding away, even pulling them out, etc. It just saves you time. This is because the parts are built up. They're sustained by the loose plastic powder. So the powder that's not sintered remains in the loose powder form, and that acts as the self-containing support structure, almost like packing peanuts in a box that you would ship via UPS, FedEx, etc. Therefore, the entire build volume can be packed with several parts. You can stack them, you can pyramid them, however, they just must fit within the build volume, and that way you're able to be more efficient with your printer. It's kind of like the dishwasher. I'll give this analogy many times. You would not run the dishwasher for just one plate. You would like to run it for 10, 20, 30, maybe even 40 plates if you have a large dishwasher. It's the same idea. If you can fit more than one print in your printer, you're going to do that. And there are software programs that I will touch on in future episodes that help you with that. As I mentioned before, the show notes can be found at structural-md.com/P004. There you will find a link to several YouTube videos. They're not very long, but they might be very beneficial to help provide some visual context for this process, which I am trying to verbally describe to you via words. So it might be a little bit challenging to understand, but definitely seeing something online will certainly help you with that. Plus, this process is super engaging, very interesting. Laser sintering can handle all kinds of materials, from composite, plastic, and sand. Obviously, within plastic, there are many different polymers that can be created, and I highly encourage you to check them out. There will be a table in the show notes. I'm not going to sit here and just list off material after material after material. So what is laser sintering used for? Like a lot of things with 3D printing, it's used for prototypes, support parts, and small series parts. The great thing is, it's a lot quicker when creating new parts because instead of having to go back and remake the mold that you used, you're able to simply tweak a couple lines on AutoCAD or whatever drawing system that you use, reprint it, and form fit it again. You can also perform functional testing. Like all things in life, there are advantages and disadvantages to everything. Laser sintering is no different. I like to look at the bright side first, so let's take a look at some of the advantages. Well, for one, laser sintering can manufacture parts in standard plastics with good mechanical properties. What this means is when compared to the baseline, which would be the traditional way of manufacturing plastic parts, the mechanical properties do not suffer. They're basically on par, if not better, than the other process. For small lot sizes, laser sintering and really almost additive manufacturing in general is price competitive and often the cheapest solution. For example, going to a manufacturer to have them create or produce 10 parts is going to be rather expensive because the manufacturer is going to have to get special tooling, a mold, whatever, to create your part, and it's really not worth their time to alter their assembly line to make your special small part. And until additive manufacturing came along, you either had to not get that part created, fork over a lot of money. All right, we have to do it. Let's take a look at these disadvantages. Now, when it comes to surface finish, laser sintering parts don't have that same characteristic as their injection molded counterparts. And that's true with a lot of things in additive manufacturing. While they may be able to be produced in a quicker manner in terms of prototyping and the whole design process overall, the surface finishes aren't quite on the same level. The mechanical properties, yes, they're typically pretty similar. And the surface finish, it's just not quite there yet. Maybe in a few years, we'll get things figured out. But you can really kind of see the layers of the part. The last part of the show will be the additive slices. So again, these might change from the time you hear this podcast, but they're up to date as best I could at the releasing of this podcast. The maximum build envelope is 550 by 550 by 750 cubic millimeters. The minimum feature size is 0.15 millimeters. The typical tolerance for a part is plus or minus 0.25 millimeters. And again, this can be improved through post-processing techniques, also improving the surface finish. And then your minimum layer thickness is 1/10 of a millimeter. I want to thank you guys for listening to this episode. If you have any questions regarding 3D printing, how it can help your business, whether it's in regards to this process specifically or other processes, if you'd like me to give a presentation to your professional society, etc., and so forth, you can always find me on the website at structural-md.com. I'll be sure to respond to your email as soon as possible. In addition, all of the show notes can also be found at structural-md.com/P004. Thank you again for listening, and I look forward to speaking with you guys on episode 005.